Welcome back. In the previous lectures, we drew inferences from the qubit evolution about the time dependence of the Hamilton operator and the statistical operator. In this lecture, we discuss these matters in a general setting. So, after going through this qubit example of the two-level atom, let's take another look at these equations of motion from a more general point of view. So we have the Hamilton operator which stands for the energy of the system. We use the letter H for that. And then we have the Schrödinger equation, and I'm writing down the version for a bra at time t, characterized by some quantum numbers which themselves do not depend on time, and then this time derivative is given by that set of quantum numbers at time t, and the Hamilton operator acting, and that's the Hamilton operator that refers to time t. Now we also have the Heisenberg equation of motion, and that's for some observable, where we say there is the total time derivative of the observable equal to the parametric time derivative plus the dynamical time derivative, which we have given in terms of the commutator of the observable with the Hamilton operator. So I just write this in a compact way as the commutator of observable A and the Hamilton operator at time t. But now let's be a bit more specific about details. So in the example that we discussed, we had the dynamical variables, which were the Pauli operators x and y and z, which we can combine into the Pauli vector operator, for which we use the letter sigma, and so forth. Now, more generally, we have a list of dynamical variables. So there is a variable a1, which depends on t, a variable a2, which depends on t, and so forth. There could be quite a few of them, so like the x and y and z for the qubit, but if we have two qubits, then there is two x's, two y's, two z's, and so forth. So there could be many of those, and I will just collect them in a list and write a of t for this list of dynamical variables. And then the Hamilton operator will be a function of these dynamical variables, and perhaps it also has a parametric time dependence. And any observable will be described by an operator, say f, which is a function of the dynamical variables and perhaps has a dynamical time dependence. So, now looking at the Heisenberg equation of motion, we would have the time derivative of this function of the dynamical variables equal to the parametric time derivative of that function plus the commutator with the Hamilton operator. And so now here the operator is a function of the dynamical variables, perhaps with a parametric time dependence, and so is the Hamilton operator. So just to be absolutely clear, this parametric time dependence differentiates this t only, and the total time derivative differentiates the t of the parametric time dependence, but also the t in the time dependence of the dynamical variables. So this is the total time derivative, which has two pieces, the parametric time derivative and the dynamical time derivative. So here, the Hamilton operator enters. So here it is important which physical system are we talking about and what are the dynamics of this physical system. As we have seen in the example for the two-level atom that we looked at in the previous lecture. Okay, so we have our list of dynamical variables. The observables, F, are functions of that, and perhaps a parametric time dependence. Hamilton operator, that refers to time t, is a function of the dynamical variables at that time and perhaps has a parametric time dependence. And so we have the Heisenberg equation for the total time derivative of any function of the dynamical variables in terms of the time derivative with respect to the parametric time dependence and the dynamical time dependence. So let's look at some special cases. First of all, there's the Hamilton operator itself. What's the total time derivative of the Hamilton operator? Okay, so surely there's the parametric time dependence. And then there is the commutator with the Hamilton operator, but the commutator of the Hamilton operator with itself, that's always zero. So it stops here. So we learn that the total time derivative of the Hamilton operator is zero if there is no parametric time dependence. So a Hamilton operator that is only a function of the dynamical variables and has no parametric time dependence, meaning that at different times it's the same function of the variables, that Hamilton operator does not change in time. Another special case is that of the dynamical variables. So what if I look at the time derivative of one of these dynamical variables? Let's say the one with index j. Okay, so now that as a function of the dynamical variables is just itself. So there is no parametric time dependence. And so we only have a dynamical time dependence. So we just get the commutator of that one variable from the list with the Hamilton operator that involves all of the basic dynamical variables that we have in this list of dynamical variables. And then another special case is that of the statistical operator. Now remember, the prototype of a statistical operator is just the ket bra that refers to the preparation of the system. So by its nature, it is not a quantity that depends on time. So there is no total time dependence of the statistical operator, which we now also view as a function of the dynamical variables at time t and the parametric time dependence. So what do we have here? Well, we have the parametric time dependence of rho, which is, as I said, a particular function of the dynamical variables and the parametric time dependence. And then there is the dynamical contribution to this time derivative, which is the commutator of the statistical operator and the Hamilton operator. So here we have no total time derivative, which means that the dynamical time derivative and the parametric time derivative compensate for each other. This is very often written in the way that we say the parametric time dependence of rho. And I remind you that derivative speaks only about how the function of the dynamical variables depends on which time we are talking about, and does not talk about the time dependence of the dynamical variables themselves. Then this is equal to, and now there is a minus sign, which I incorporate by remembering that negative 1 over I is just I itself. So here we have this statement for the statistical operator. And since this is a statement only about the parametric time dependence, it doesn't actually matter at which time we take the dynamical variables, whether these dynamical variables that appear here, these operators refer to the time t with respect to which we take the parametric time dependence, or they refer to another reference time. That plays no role in this equation. So now let's turn our attention to the Schrödinger equation. Rather than talking about some arbitrary bra, I will talk about the bras that make up a basis. So let me call this the bra B1 at time t, B2 at time t, B3 at time t, and so forth, maybe all the way to Bn time t if there are n such bras in a basis of bras. We take the time derivative of every one of them, and then of course this says that I have to apply the Hamilton operator to each of them on the right. But that just means that I have this whole column of bras all the way to Bn t, and the Hamilton operator at time t applied on the right. And the Hamilton operator at time t, I remind you, is a function of the dynamical variables and maybe has also a parametric time dependence. But now, having this system here, we make use of the completeness of this basis B and also introduce the list or the row of basis kets, B1, B2, and so forth, all the way to Bn t for the kets. And then for the completeness relation, we multiply with the column of bras. And just as a reminder, this product of this row of kets and the column of bras, that's just equal to the identity. So I'm just multiplying with the identity. But now, what we have here is a matrix that represents the Hamilton operator with respect to this basis at time t times the column. So let me write h t, script h, for this n by n matrix for the Hamilton operator h, and then we continue with this column of basis bras. So originally we have the time derivative equal to the column Hamilton operator acting on the right, and then this becomes equal to matrix that multiplies the matrix that represents the Hamilton operator multiplying the column on the left, as the matrix should. So for the Hamilton operator, the natural way of acting on the bras is from the right, but for the matrix multiplying the column, the natural way of doing this is the matrix to the left of the column. Now we take it from here. So I repeat, time derivative of this column of basis bras is equal to the Hamilton operator applied to each of those bras from the right, and that again is equal to the matrix that represents the Hamilton operator acting to this column on the left. And so I should note that this matrix, since it's a matrix that we get by sandwiching the Hamilton operator at time t with this column of basis bras on the left and the row of basis cats on the right. This Hamilton operator will not depend on time if there is no parametric time dependence. So is independent of time t if there is no parametric time dependence in the Hamilton operator. Then this will just be a matrix which is the same, just a matrix that is the same for all times. So now this is a statement about this column of basis bras. We draw a conclusion now about the corresponding statement about the wave function that describes the state ket. Now the state ket is equal to the row of basis kets times the column of probability amplitude, psi 1, psi 2, all the way to psi n, for which we just write the symbol psi of t, so that refers to this column. And what is this column? The psi of t is equal to the B1 bra, forming a bracket with the state ket, and so forth to the Bn at time t bra, forming a bracket with the state ket. And so here all the time dependence comes from these bras, again making up a column. And so we can just translate this statement about the time derivative of this column into a statement about the time derivative of this column of probability amplitudes, namely that I h bar d by dt psi of t. So this list of probability amplitudes that describe the state ket, referring to the basis that refers to time t, and therefore these probability amplitudes themselves are time dependent. So this is equal to the matrix that represents the Hamilton operator, multiplying this column of amplitudes, multiplying this wave function. So here we have the wave function, time derivative of the wave function equal to the matrix representing the Hamilton operator applied to the wave function, the column of probability amplitudes. Very often this statement is also called a Schrödinger equation. And of course it's just a variation of the Schrödinger equation that we had originally for the generic bra. Now we had the particular bras that make up the basis, and then from these bras we get the wave function, and so we have the time derivative of the wave function as a consequence of this basic Schrödinger equation for the bras. So we have a Schrödinger equation for the wave functions. In summary, what we observed for the qubit evolution about the time dependence of the Hamilton operator and the statistical operator is quite generally true and extends to other operators as well. We also saw how the Schrödinger equation for a wave function emerges. In the next lecture, we apply these insights to a 2-qubit example.